Hey everyone, so if you're streaming this, checking your email, or, saving a file, you're using the cloud. It just feels invisible, right? Almost like magic. But today we're going to pull back the curtain and take a hard look at the very real, very physical chains that hold it to the ground.
And this is the image we're all sold, isn't it? This idea that our data is just floating out there, borderless, instant, and always there when we need it. It's a really powerful and, let's be honest, a very convenient illusion.
But what if it's all just clever marketing, What if the cloud isn't floating around at all, but is actually physically chained to the ground, limited by the same real-world problems as everything else? Well, that's exactly what we're going to dig into.
Okay, so let's start with the first chain, the simple, undeniable fact that the cloud is anchored to the Earth. And this makes its global reach, well, a bit of an illusion.
Here's the raw physical truth of it. The cloud is actually millions of tons of concrete and steel, these massive, immovable data centers. It's thousands upon thousands of miles of fiber-optic cables buried under our streets and our oceans. All of our data has to physically travel through a surprisingly small number of these locations. So forget the fluffy metaphor. The cloud isn't a cloud, it's a factory.
And because it's set up like a factory, all that data gets funneled through these geographical bottlenecks. It doesn't just magically appear anywhere in the world. It has to travel a physical path through major hubs like Ashburn, Virginia, or Frankfurt, Germany. So if one of those hubs has a bad day, entire continents can feel it. And this leads to a really common and, frankly, a very dangerous assumption. Let's say you're a developer and you do the responsible thing. You set up your system in two different cloud regions for redundancy. You think, hey, if one fails, the other one just takes over. Sounds perfect, right?
But here's the catch. On paper, in the world of software, you've got two perfect independent backups. But in the real world, the fiber optic cables for both of those systems are often bundled together in the exact same physical trench. All it takes is one misplaced backhoe during construction, and your entire redundant system is completely offline.
So, the crucial takeaway here is this. Your software might be resilient, but geography isn't. The cloud just can't abstract away a physical cable getting cut. This creates these hidden, single points of failure that can undermine even the most carefully designed systems. So, okay, even if the core data centers are running perfectly, there's another chain holding the cloud back. It's called the last mile problem. And this is the exact point where all that power and potential can just come to a screeching halt.
The last mile is that final, absolutely critical connection between the vast, high-speed internet backbone and you. It's the wire that runs to your house, it's the cell tower your phone is connecting to, and it is, so often, the most fragile part of the entire system. I mean, just imagine a piece of data on its journey for a second. It leaves a hyper-efficient data center, zips through a regional hub, gets routed at a local exchange, and then, bam, it hits that final step, the last mile. This is where all the promises of speed and reliability that were made back in the cloud can completely shatter.
And why do they shatter? Well, because in many parts of the world, running fiber to every single home is just way too expensive. Cellular coverage can be patchy, totally unreliable, and even if you have a great signal, an unstable power grid can make the whole connection worthless anyway.
Think about it. It really doesn't matter if a data center costs billions of dollars to build. All that power is completely useless if the final connection to the user is broken. At the end of the day, the cloud's reach is only as strong as its weakest final link.
And that brings us to our final chain. This is one that no amount of brilliant engineering can ever break. The inescapable laws of physics. Let's talk about the tyranny of distance. So, data travels through fiber optic cables at about 2/3 the speed of light. Sounds incredibly fast, right? But the planet is big. Sending a signal from London to Tokyo and back just takes time. That delay, what we call latency, is an unavoidable consequence of distance. And it's not like it's a straight shot either. Every single time your data hops from one piece of network gear to another, a few milliseconds get tacked on. Each segment of undersea cable adds a little more. And if you hit network congestion, it's like being stuck in digital rush hour traffic. All those tiny delays, they add up and they add up fast. Now look, for streaming a movie, a tiny delay really doesn't matter much. But for a high-frequency financial trade, that delay literally means losing money. For a remote surgeon controlling a robot, it could be absolutely catastrophic. This latency isn't just an annoyance. It causes critical systems to fail and data to become unreliable. So, let's bring it all together. When we really look past the marketing slogans, a much more grounded, a much more realistic picture of the cloud starts to form.
When we put it all together, this new picture emerges. First, we have to accept that the cloud isn't some abstract, magical concept. It is a physical thing. And it's not spread evenly across the globe, not by a long shot. It's intensely centralized in just a handful of key locations.
And all of this relies on an immense, and as we've seen, a surprisingly fragile physical infrastructure.
And this whole system is completely dependent on a constant, high-quality connection to the real world just to even function. And that brings us to the core truth of this whole explainer. The cloud, for all its software magic, is only as resilient as the physical ground it is built on.
So this is the reality we're facing. The cloud is incredibly powerful, but it's not universal. It's limited by geography, by economics, and ultimately by the laws of physics. The real challenge for the next decade, then, is a pretty big one. What is it going to take to finally break these chains?